All right, so this video is going to serve as an explanation of homotopic, enantiotopic, and diastereotopic protons in an NMR spectrum. Now, really what we're trying to do is to determine how many signals we will see in an NMR spectrum when given a specific molecule. So each of these homotopic, enantiotopic, and diastereotopic protons will give a very specific signal. Okay, and so we want to see what's going on with this. Well, first let's take a look at homotopic. Now, homo meaning same, right? So homotopic protons are basically going to give one resonance, and they are equivalent protons that give one resonance or one signal in the proton NMR. Now, how do we do this, or how do we determine this? Is basically when we substitute two hydrogen atoms of a CH2. So we're really, for all of these homotopic, enantiotopic, and diastereotopic protons, we're really only looking at the CH2s because the process requires substituting two of the hydrogen atoms by some atom Z. It doesn't really, it's generic. And then when that happens, if we form the same product, then those two protons of the CH2 are considered homotopic. They are equivalent protons, and they give one resonance. Okay, so the example would be down here, where if we really just kind of substituted one of those, let me get it green, one of those hydrogens for a Z, and then we substituted the other one for a Z. Remember, Z is generic. If you wanted, what you could do is actually swap this out for, let's see if this green works well. Hopefully that green is okay for you guys. I like to use green for chlorine because that's the color. It's kind of yellow-green. So now identifying whether or not these are the same might be the tricky part, but you can think about it in terms of nomenclature. So this is a hexane parent chain, and if we were going to name this, what would we name it? Well, let's focus on the one on the left, right? Correct. This would be 3-chlorohexane, right? And so would this one, 3-chlorohexane. And remember, there's a symmetry element here, and so if you can pretty much slice down the middle of this particular CH2 and get the same thing on the left and the right, then that symmetry element in fact means that those are going to be equivalent protons. And so but then you can further identify them as homotopic if you wanted to substitute out for Z. And now I guess the naming aspect of it is important just to differentiate between maybe constitutional isomers versus similar molecules or stereoisomers. So really this is what we're getting at, stereoisomers. Enantiotopic protons are, again, when you're substituting two hydrogen atoms by Z and you form enantiomers. So if they are in fact forming enantiomers, equivalent protons giving one resonance is what we get. Okay, so remember, one resonance means one signal. Now, just to kind of let you guys know or remind you, an enantiomer is a type of stereoisomer, and it is basically when you have a carbon with 4 different groups on it. Okay, so let's be more specific. So an sp3 carbon with 4 different groups on it. It could be, you can think of them as substituents, and so that'll be, I think in that sense it'll be more clear when I explain it in just a second, but CsP3 with 4 different groups on that carbon, okay? Now this is an enantiomer. So how does that work out when we are referring to the given hexane molecule. How does that pan out? Okay, so let me move this out of the way to give me a little bit more room. Now really what we're looking at is, let's go back to green, sorry. We're substituting out one of these hydrogens, and we're substituting out the other hydrogen, right? So let's put a Z for the other hydrogens, and now what we have here is enantiotopic protons by definition for these guys. And the way we can see this is because if we look at this particular carbon right here on both molecules, we can see that let's see, on the left we have a methyl, okay, and then on the right we have a propyl group. Remember I was saying you can kind of view these as substituents. And then we also have a Z and a hydrogen, Z and a hydrogen. So those are definitely 4 different groups, right? And so by definition, there should be enantiomers. And it would perhaps, it's important to actually remember that these hydrogens and the Z are actually projected into the plane of the board or out of the plane of the board, right? So we can give them wedges and dashes, in other words. So let's give this guy okay, and so since they are basically projected in different directions, they are considered enantiomers or stereoisomers. Similar to like cis and trans isomers, they're projected in the same direction or in an opposite direction, different direction. And so this is the 3-dimensional aspect of organic chemistry that makes it so fun. Now, that's pretty much enantiomers in its basic form. So that's really what you're looking for when we're talking about enantiotopic protons, okay? Now, there is a video coming with a deeper explanation of enantiomers and stereoisomers in general. So, but in its basic form, that's all we're looking for. And then we can identify those as enantiotopic protons, and they give 1 resonance. Okay, so now let's focus on the next term. So diastereotopic, very much related to enantiotopic protons. We do the same process. We have a compound, and when we substitute 2 of the hydrogen atoms by Z, we form diastereomers. And if that's the case, then we have inequivalent protons. Okay, so let me actually highlight this one right here. Inequivalent protons giving 2 resonances. Okay, whoa, 2 resonances, as opposed to the other 2, which were equivalent protons giving 1 resonance. Now, really what we're looking at is some compound. And now I'm just going to give it some wedges and dashes, just so that we're very clear as to what's going on. Okay, so if we had this particular compound, then we kind of separated it into these 2. Now let's draw in our Z, because we're substituting for Z. Okay, now here's the thing. Before, when I was discussing homotopic, I mentioned the fact that if we were to kind of slice the CH2 or the molecule in half through that CH2 bond, if it is a plane of symmetry, meaning we get the same thing on the left as the same thing on the right, then those 2 hydrogens are going to be equivalent. So the enantiotopic, that wasn't the case. If we were going to slice this in half, we would get different things on the left and the right. But that means we need to look a little bit further, right? And so if we were going to look a little bit further, we would see that we only have one carbon with 4 different groups on it after we substitute for Z. If we do that in this compound right here, let's say we slice down the middle. Now it's very different on the left as it is on the right, right? So the left and the right have, one has an OH on it, the other doesn't. So they're different. So far there is no plane of symmetry about that CH2 bond. Now what we want to do is look further. So what we want to do is see if there's another carbon in there that has 4 different groups on it. Now if you look closely, you can see, or not even that close, you can just notice that there's a hydrogen and an OH on this particular carbon. We also have a methyl on one side and then a propyl on the other. So that is actually one of those sp3 carbons with 4 different groups on it, which we call a stereogenic center. Since this particular molecule already has a stereogenic center in the starting molecule, if we can substitute out, if we have any CH2s actually, then we will have diastereotopic protons. Okay, so the key here is if there is a carbon that has 4 different groups in it, to start, if you have a CH2 in that compound, then you probably have diastereomers once you substitute out for Z. And really what we're looking for is if we have a stereogenic center, which we identified as that sp3 carbon with 4 different groups on it, then we have, and when we substitute out for Z, what we did was we created a new stereogenic center, right? And so that's really what the definition of a diastereomer is. It's 2 different stereogenic centers, aka sp3 carbons with 4 different groups on it, and they are more or less projected in the different direction. So we have an OH pointed out at us and a Z pointed out at us, as opposed to an OH pointed out at us and a Z pointed away from us. And so that's what we mean by projected in a different manner, different 3-dimensional orientation. Okay, now let's go over another way that we can kind of discuss basically the proton signals. Okay, so we have a question: how many proton signals would you expect for each compound? Okay, so first what we really want to do is look for CHs and CH3s. This is me breaking it down, how my thought process. So CH3s and CHs, if they're the only ones, then they're definitely going to be their own signal. But if they're not, are they bound to the same thing? Meaning, this right here is a CH3, right? So CH3, CH3. Now, we also have a hydrogen here. That's just a CH. This one happens to be the only one, right? And so that means that that's for sure going to be its own signal. Let me draw this as a different color. Okay, that is its own color. I'm going to give it some stereochemistry here. Okay, now let me give this guy some stereochemistry. This helps kind of identify this enantiotopic and diastereotopic protons. Now, looking at those CH3s, what I mean by, since they aren't the only ones, they may or may not be equivalent protons. And so what we want to do is see what those CH3s are bound to. And what I mean by that is, what's this carbon bound to? Well, it's bound to a carbon, but that carbon is bound to 2 hydrogens, right? So this one on the left, that is bound to a carbon as well, but that carbon is bound to a chlorine and a hydrogen, so that's different. And so therefore, these are going to be different as well. Okay, so that's 2 signals from those 2 separate CH3s. But all the hydrogens on the CH3s are always equivalent. Okay, so remember, the only time we can have different hydrogens that are bound to the same carbon is when we have diastereotopic protons, and that's when we have a chiral center existing already. And that brings us to the last kind of like step in identifying if the proton signals are equivalent, so, or how many we have. So now what I do is I look for CH2s, okay, found it, and also I look for stereogenic centers. So again, stereogenic centers are the carbons, the sp3 carbons with 4 different groups on it. Now we have clearly identified this guy as a stereogenic center because it has a chlorine, a hydrogen, as well as a methyl on one side and an ethyl on the other, right? So it's getting a little crazy now. I'm gonna kind of delete some stuff. So now, since we have identified that as a stereogenic center, I'll put a little asterisk there. If there's no stereogenic center, then all the CH2s would have been the same. However, and they would have given one signal. However, since there is a stereogenic center, then we want to see if there's no plane of symmetry bisecting the CH2 group, then they are inequivalent and give 2 signals. And so really what we're doing is we're slicing it down here. We can see that we've clearly got a different group on the left side and the right side. And so those 2 hydrogens would be diastereotopic. You can also substitute them each for a Z, and that would give you 2 different compounds in terms of stereoisomers. But in my opinion, it just seems easier to, once we get a better grasp of diastereomers and enantiomers, it just seems easier to bisect it. If we have a stereogenic center and we have a CH2 and we bisect that CH2 and there's no plane of symmetry, then they are diastereotopic protons, meaning I have to erase this right here because that is one signal, and let's see, what color do we want? Orange. And this is another. Hopefully you can tell the difference. Let me just do that in blue. So really what we have is one for the triangle, one for the square, 2 separate ones for the circles, so that's 4, and then 5 for the pink proton, which I can do like as a diamond. So 1, 2, 3, 4, 5. 5 signals. Okay, now let's take a look at the compound B. Look for CHs and look for CH3s. Okay, so we found there's a CH3, there's a CH3, and then there's also a proton here. Let me draw that more appropriately. All right, so there's the only CH that's there, so this is going to be its own signal. The CH3s are in question. You can see those are very different because this CH3 is bound to the oxygen directly. And here, what do I want to do? What shape do I want to do? All right, that CH3 is different than this CH3 because that's bound to a carbon, then bound to that oxygen. So they are not the same. Now what we want to look at is these guys, the CH2. So first we want to look for a carbon that's bound to 4 different groups. Now, if you can't tell right away, we've already kind of messed with that. That's this carbon right here that I'm drawing an asterisk by. That carbon is bound to an oxygen, bound to a CH3, it's bound to a hydrogen, and it's also bound to a CH2 with the chlorine on it. So that is a stereogenic center. It's an sp3 carbon with 4 different groups on it. And so now we get to look at that CH2, see if there's a plane of symmetry, bisect through that CH2, there's no plane of symmetry, and therefore that is diastereotopic. Okay, so we would in fact have 2 separate signals for that. So that's 1, 2, 3, 4, 5 signals total. Okay, now let's take a look at this one. This is actually, yeah, let's just do it. How many signals do we get? Let me do that so I can draw my hydrogen in. Well, I've been keeping with the pink theme. Gotta look pretty in pink with that single hydrogen. Boom. My CH3s have been liking the green. So let's take a look at those. Now we've only got one CH, right? So that one is going to be its own signal. The green, we have this particular CH3 is bound to a carbon that's directly bound to a bromine. So that's going to be different than that CH3. And you can think of them in terms of acidity too, right? Like that CH3 is bound to a carbon that's directly bound to a really electronegative atom, and so the acidity of that proton is going to be different than the CH3 on the other end, right? And so when you're thinking about acidity of protons, for me personally, I like to think of them in terms of like electron density, because being next to an electronegative atom means that that bond is more polar, and so it's that proton has got a greater delta positive charge on it. If it's got a greater delta positive charge on it, it's got a different amount of electron density around it, and that's really what we're talking about when we are talking about proton resonances. It's all about remember we have the B naught, where we have that applied magnetic field, and then that applied magnetic field is affected, or it's like the protons are either feel all of that B naught, or they feel some of it. And when they feel some of it, that's because of the amount of electron density surrounding that particular proton, and so that's ultimately leading back to the acidity of that proton, right? More or less electron density. Because remember, if we have electron density around those protons, they create their own magnetic field and they oppose the applied magnetic field, and that is called shielding. And if we have less electron density around it, it's deshielding. Okay, just a quick reminder of all that. Super fun stuff. Throw that in your brain again. Really, so we've identified the CH3s as separate, right? Now, what we've got here is we've got to look at the CH2s now. So we've got CH, CH, ooh, then another one. There's the CH there and there. Sorry, the CH2 there and there. Now, if we have a stereogenic center, then we've got to look more closely. There's a stereogenic center there. Okay, so that means if we can kind of slice through here or here and create, and there's no plane of symmetry, then those protons would be diastereotopic. And so let me see if I could just come up with more colors. We've got the red, the blue. I'll do poopy brown for that proton. And then what do we got? Ooh, we got like pastels. I'm gonna go with this green right here. That looks kind of cool. I think that's pastels, right? Don't judge me on my colors. All right, so that's 1, 2, 3, 4, 5, 6, 7 signals. 7 signals. Okay. Now again, those CH2s are diastereotopic because there is a stereogenic center, and if we were going to exchange out one of those protons with a Z, we would create a new stereogenic center, okay? And that's pretty much it. So that is a lot of information on homotopic and enantiotopic and diastereotopic protons, but once you get a few practice problems in, I think you'll get it. Gotta finish with that last minute joke real quick. How many wizards does it take to change a light bulb? Depends what you want to change it into.
That is so funny.